inaugural astronomy seminar of the 2016-2017 year. Very fortunate to have Charles Steinhardt visiting, who is moving from across the country. He's moving from Caltech, driving all the way to the University of Copenhagen in Denmark. And he agreed to stop off to meet with some of us today and tell us some about the work he's been doing. Dr. Steinhardt finished his graduate work at Harvard, where he has both an astronomy graduate degree and a master's in computer science. So you should definitely listen to what he has to say. Before taking postdoctoral positions at TAMU in Japan, and then now he's at Caltech and IPAC in Pasadena, en route to University of Copenhagen. So without further ado, thanks, Charles.
Yes, thanks for inviting me. It's the first time I had a chance to be out here, so I really appreciate the opportunity. And what I'm going to do is tell you about some of the things that we've been working on for the past few years in thinking about the evolution of galaxies, particularly toward high redshift, and some seemingly fundamental puzzles that might be coming out of that, suggesting hopefully something interesting is going to happen in the next few years. So when we think about the story of a galaxy, we really divide it kind of into three phases that happen sequentially. So the first thing that happens is we just have to assemble our initial ingredients. And this just means you start with primordial fluctuations, you add gravity, eventually we get all the material in one place that's going to become a galaxy. Once that happens, then we have to take those ingredients and actually make a galaxy out of them. So we make stars, we make a central supermassive black hole, and all the other things that we see in galaxies. And then by today, at least for the most massive galaxies, all of these processes have stopped, and we end up with something that's primarily passive and quiescent. And each of these three phases, we really have come to study in three pretty different ways. The first of these has been, to this point, entirely the domain of theory. I'm going to mention a couple places that we're just starting to get the observations into this initial assembly, but to this point, this is really something that's being done primarily through numerical simulation. The second of these, as I'm going to show you, is a place that we've really made rapid gains in the past decade or so. And we're primarily studying objects mostly through photometry, and in some cases, if we're really lucky, we might have some spectra. Okay? The last one of these is really the only point at which we're able to start resolving galaxies and learning more about the details of what's going on. For everything else, we're really inferring properties based on what we've learned about this last stage, and hoping that the things that we infer still turn out to be good enough. Okay, but with that, there have been a few things that we've been able to learn, and perhaps one of the most important over the past decade has been something that we've come to call the star-forming main sequence. And this is maybe a little bit of a misnomer in the sense that this is not the same thing as the stellar main sequence. Okay? What this is telling us that at any fixed redshift, there's a tight correlation between the existing stellar mass in a galaxy and the rate of new star formation. And I should stop for a moment here and point out that even though this looks like a very simple description of what's going on, perhaps this should already be kind of surprising. That is to say, if I were to ask you, what are the things that you expect are important to determining the star formation rate in a galaxy, you'd probably give me a long list of things, right? You might talk about the environment. Maybe the merger history is important. Certainly you'd expect it should be important whether we're in the middle of a major merger, or even a minor merger, right? Are we in a void? You might expect the metallicity is important. You might expect the age of the stellar population is important, or something about the star formation history, something about the supernova rate based on that. What we get here seems to be much simpler. What we get here tells us that in fact, if you look at everything that we select as a star-forming galaxy, and we just tell us the redshift, that says it lies on one of these plots, tell us the mass, that's enough to at least approximately determine the star formation rate that we observe for almost all of these typical massive galaxies while they're forming stars. So we understand this observationally. We really do not understand why this is true theoretically. Okay? But we understand it observationally. And I'm showing you one example here. But actually, since 2007, there have been a couple dozen, and now there are about 5 more studies actually since that I can add to this list. There have been a couple of dozen different studies that are all looking at the star-forming main sequence. Okay? They're looking at the star-forming main sequence in different ways, so they have different star formation rate indicators, they have different ways of selecting star-forming galaxies, and all of them are giving us, at least qualitatively, the same answer. Namely, first off, that there is a main sequence at every redshift where we've been able to test it. Okay? And then also they agree, at least qualitatively, on how the redshift evolution changes the main sequence. That first, toward high redshift, we're finding that at fixed mass, the star formation rate is going up. Or often we talk about this in terms of the star formation rate per unit mass, or specific star formation rate. Okay. Well, this kind of makes sense intuitively. This simply says that early in the universe, when a galaxy is young, it starts with a big reservoir of material that can be made into stars. And we probably just deplete that over time. This other one is a little bit more puzzling. That as we look toward high redshift, and you look at the most luminous galaxies, they're actually becoming more luminous and more massive toward high redshift. We don't necessarily know whether this is true for the galaxy population as a whole, because we run into selection problems. We're detection limited at high redshift. But at least for the most luminous ones, it somehow seems like they're becoming more luminous early in the universe. And I'm going to come back to this one a little bit later, and why we should think about that as being so surprising. Okay? So we agree on all of the details qualitatively. Quantitatively, it's been a little bit more complicated. So when we look at a star-forming main sequence, one of the things that you might measure is you just might measure this slope. And if I look at these different studies, and I look at the slopes that they report, and I ask, okay, is the slope increasing or decreasing with time? Okay, well, with time, what I might find is maybe it's increasing or maybe it's decreasing. I guess there's actually not so much support here for it being constant. But the point is there's this sharply increasing disagreement as we look early in the universe and as we look toward high redshift.
I guess I missed it. You haven't defined what a star-forming galaxy is, except a forming star, but there must be, you're not including elliptical galaxies in this, right?
We're including, so generally these are just things that have a young stellar population. So it's going to be some color cut.
So there is a selection effect.
There is a selection effect in star-forming
galaxies.
galaxies.
Is a function of redshift.
The selection effect is a function of redshift, and for these different studies, there are actually many different selection criteria that people are trying. So so if we ask why are the slopes changing, okay, we might think that this is because we have different ways of trying to select what a star-forming galaxy is, or because we have different ways of trying to measure the stellar mass or the star formation rate, or something like that. Right? So perhaps this increasing disagreement at high redshift really just tells us that we calibrate all of these things against each other at low redshift where we can, but it's not so easy at high redshift, that these relationships start to break down. And that's what I thought was going on. And I had an excellent student, Josh Spiegel, who's now a grad student at Harvard. And we went through all these and sort of tried to look through the details and figure out what was going on. And we discovered that there's actually a much simpler explanation. So in addition to different selection criteria and different ways of measuring these properties, it turns out that these studies also do things like assume a different IMF, assume different extinction laws, in a few cases even assume different cosmologies. Okay, I can't tell you which initial mass function's right. I mean, that's a difficult problem in its own right. But what I can certainly tell you is that if you look at results using different IMFs, you're effectively reporting them using different units. Okay, so if we really want to compare apples to apples, what we need to do is we need to just convert these and put them all on a common basis. And so that's what Josh and I did, is we went back and we just essentially adjusted everything to a common set of units. Okay, and they agree remarkably well. So what I'm showing you here is a little bit different view. I've actually picked a fixed mass, in this case 10 to the 10.5 solar masses for the stellar mass. And I'm showing you what different studies get for the star-forming main sequence. These error bars actually are a spread of the main sequence and a redshift range, is what I've drawn here. Those aren't uncertainties. But these are different measurements of the star-forming main sequence at that mass. Essentially, the star formation rate is a function of time. And what we find is actually this remarkable agreement. Okay, first off, that at a fixed redshift, different studies give you basically the same answer. And second, that we even get this simple description of the redshift evolution. So this is a log star formation rate against linear time. So this is an exponential decay. We find this remarkably simple, well-fit description of what the decay is. And just to show you that I'm not cheating, here's what this looks like for a few different slices at different masses. I should mention, by the way, that another way in which this is not like the stellar main sequence. For the stellar main sequence, you can really think about this being something fixed, where you can evolve along it, right? In this case, it's worth noting that as a galaxy grows, the star formation rate means that the stellar mass is increasing. So an individual galaxy will not take this track. Rather, it might start here and then end up here, and so forth, okay? But still, so in other words, the idea that this is an exponential decay is not necessarily a guarantee that an individual galaxy has the same exponential decay. An individual galaxy might do something a little bit more complicated. This is really something three-dimensional, and we're showing you a few different projections of it. Okay, but the real thing that we should do when looking at this plot is basically we should be celebrating, right? As observers, we can declare victory here. We've taken this problem and we've now learned that if we measure it different ways, we select galaxies different ways, we measure the key quantities different ways, they all agree over a wide range of redshifts. This is a solved problem observationally. It's not a solved problem theoretically, right? We still don't understand why we have this behavior. And to some extent, that should even be more worrying, because usually if we want to kind of get at the theory of this, right, we need as much information as we can possibly get. And this is a really not only is this a really simple description, but in some sense it means we're now using all of the information. You know, measuring additional star-forming galaxies isn't really going to help us. They're just going to take this simple relationship and establish it further. Sorry, did you have a question? Oh, sorry.
I do have a question. These aren't measured quantities. These are interpreted for measurements.
These are inferred quantities.
You haven't said anything at all about possible correlation errors. I mean, if you have a correlation between different parameters, x and y, you can also induce a linear slope like that. It's important for me to understand what you actually measure and what the interpretation of the measurement is when you say that it's understood. Because what's understood is I would say what's understood is not necessarily these quantities, because they're interpretations of what you observe.
Yeah. So I think if I wanted to take as conservative a view as possible, which is always a good question to ask observationally, right? As conservatively as possible, what I can say is essentially there are strong correlations between red light and blue light. So there are certain features of the spectrum which, as you evolve to different galaxies at the same redshift, certain relationships between red light and blue light hold. And if we're right that sort of the initial mass function is approximately constant over time or something like that, then it probably would be reasonable to interpret those as a stellar mass and a star formation rate.
And it says that under a fixed set of assumptions.
Yeah, at a fixed set of assumptions, this is what happens. If it turns out that those set of assumptions break down over time, then at some point, this thing that I'm labeling SFR won't quite stand for star formation rate. It'll essentially stand for some observable thing, which at low redshift looks a lot like star formation
Of course,
rate.
the absolute values could also shift depending on assumptions that
Yes.
the models normalize. You chose it.
That's right. I picked one way of normalizing it. So we'd like to explain this, right? And I think the best way to explain it essentially is to say, well, look, you've got these three things that we know, that we observe about star-forming galaxies. I want to find a way into explaining it. What I probably need to do now to get new information is to look for objects that are not on the star-forming main sequence. Look for outliers that for some reason, there are a handful of objects that are in a major merger very near a 1-to-1 ratio, and they have star formation rates much higher than the main sequence. Maybe I should look for dwarf galaxies that aren't yet on the main sequence, or I should look at galaxies that have turned off, or something like that. And the direction that I've been going with this in the past few years is to think a little bit about these last two things and what the evolution looks like toward high redshift. Because toward high redshift, things are becoming more massive, and they're getting higher star formation rates, okay? But this can't go on forever. At some point, at high enough redshift, we're going to get back into this era of initial assembly. And these things are going to stop, and the main sequence is going to break down. And then hopefully if we can get into that era, maybe we're going to be able to learn something about why we have this main sequence-like behavior in the first place. So that's the idea that it prompted both candles, which a lot of people in the room are probably familiar with, and SPLASH. So the difference between SPLASH and candles, essentially, first off, is the Spitzer data that we have, about 2,500 hours of Spitzer time. But then more generally, it's a little bit of a strategy difference, that we're not going quite as deep as candles, but we're going over a much wider area. So in some sense, the two surveys are complementary. Candles is going to be able to go deeper and get the lower mass end, but it's not going to be able to do as good of a job at measuring the rare high mass objects. We don't go as deep as necessary to get the low mass ones, but we have a wide enough coverage area to get the high mass ones. So we're trying to kind of get the high mass end of the main sequence. At the moment, we can select this out to about a redshift of 6, and with the Suprime-Cam data that's going to come along in the next 6 to 12 months, hopefully we'll be able to push this out to about a redshift of 8 to 8.5. But at least to a redshift of 6, I can show you what happens on the high mass end. We hope the main sequence broke down. We invested 2,500 hours of Spitzer time, and we kind of get another main sequence. Okay, and not just another main sequence. Okay, but if I go back and show you what you would get from extrapolating at lower redshift, you get exactly what you would have guessed. Okay, maybe another way that I can show this, and I'm going to come back to this in a moment, but I had mentioned this mass downsizing issue. That as you go toward high redshift, the most massive and most luminous things are getting more massive and more luminous. So one way of looking at this, at the top I'm showing you this for star-forming galaxies from these different studies of the main sequence. Essentially what the high mass cutoff is where we stop seeing an appreciable number density of objects. I may not have a chance to discuss this in detail, but I can come back to the reasons I put it on the plot in questions if you'd like. I put some quasar data on here as well. But SPLASH, again, gets the answer that you would have extrapolated. So we put 2,500 hours of Spitzer time in, and we actually would have basically been able to guess the answer. On the other hand, maybe this is more surprising than it seems to be at first. And one way to think about this is to go back and try to connect it to the theory of this initial assembly phase. So to do that, I should point out that everything we're doing here so far, we're really working from luminosities. We're working from photons, we're working from baryons. But when we think about the theory, it's primarily concerned with assembling dark matter halos. So to connect this back to the theory, we have to start by looking at halo mass functions and figure out how to match the two. So what I'm showing you here is a theoretical halo mass function. Different simulations will give you similar looking answers to this, that essentially the dark matter is relatively well understood. The baryons are complicated. We don't know how to paint the baryons on. But the dark matter is relatively well understood. And what we find, okay, so I'm showing you the solid line here is a halo mass function that we would expect of redshift of 6, corresponding to the highest mass galaxies that we're seeing in SPLASH. So if it turns out that you primarily make a galaxy while you're in the process of assembling the halo, right? That you make the stars, say, in small clumps on the way in, right? Then you might expect that we should be comparing a redshift 6 galaxy with a redshift 6 halo mass function. If, on the other hand, your model for making a galaxy says that first you assemble the ingredients and only then do you really start making stars in earnest, then it should require a couple 100 million years to make the stars in those galaxies. And so then we really should be comparing more like this dashed halo mass function at redshift 8 with what we see at redshift 6. So depending upon your model, you might prefer the one or the other of these. Okay. What we're actually getting, though, is a stellar mass, not a halo mass. So we have the additional problem of asking, well, what fraction of the mass of the halo has been converted into stars? Okay, at redshift 6, I can't answer that question. Okay, I can make a best guess, though. So the best guess might be to start off by looking at low redshift. Now, at low redshift, the answer is about 10% of the baryons end up in stars. There's another factor of something like 7 to account for the dark matter. So that might be a reasonable guess for the halo mass. And if I do that, what I find is that SPLASH would tell you that there are far too many. Okay. Now if this point were down here, if this point lies below the halo mass function, that would be fine. All that says is you make the halo, and it takes a little while after you make the halo to go ahead and make a galaxy. Or perhaps that not all halos are occupied with galaxies at that redshift, or anything like that. Finding it above the line, though, is much trickier, right? That really seems to say that something's broken. You know, either we're wrong about where the point is, maybe we're overestimating the masses systematically, maybe we've blown the redshift calculation, who knows, okay? Or we're wrong about where the line is, and something in the theoretical halo mass functions is wrong. But at least one of those has to be the case. Okay, and I'll show you the Candles point as well, which is a consistent answer. The uncertainty is larger just because Candles has a smaller coverage area, so that means it doesn't get to count as many high mass galaxies. But you get a consistent answer. Now, of course, Candles and Splash are using predominantly the same techniques. So they're independent surveys using identical techniques, basically.
I mean, how much do you think things are getting to bias affect the number density measurements of galaxies as well?
So I think a better way to answer that is actually to show you this next slide, where what I've done is, so if I convert stellar masses, right, that's what we're doing with Splash.
You're saying you're taking the stellar mass, you're applying some factor to guesstimate what the halo
Yes.
mass would be, and then just say find the number density is
Right.
much higher. Okay.
Yeah, and if I'm willing to be even more optimistic,
Right.
and I'm willing to sort of say, I think I know what the stellar mass to light ratios are also, because I don't think the IMF has changed much, then I can actually take all the luminosity functions that Candles gets, and I can do the same thing, right? And then what I'm going to get, okay, so I'm showing you halo mass functions at a range of redshifts, and then these points that come from a variety of sources, but all of the high redshift ones are basically taking luminosity functions and doing this conversion. And you really get a strong mismatch. And I should point out, by the way, that there's about 9 orders of magnitude in scale here on this y-axis. So these are enormous mismatches in number density, okay? And obviously a question we want to ask immediately is, well, could we be putting these points in the wrong place, right? Could we be systematically overestimating the masses, something like that, and could that fix the problem? And so the reason I kind of want to show you these together, let's suppose that that's the case. Let's suppose that what's happening is that in fact luminosity traces mass, but we're wrong about the matching, right? Can I make the points look like the lines just by shifting them to the left? Well, no, I really can't, right? The evolution is different in several ways. I mean, the slope of course is different. But more importantly, if we look at what the halo mass functions are telling us, we look at what the simulations tell us about how structure comes in the universe, what they actually tell us is that for a given mass, structure tends to come in rather sharply. Right? If I look at, say, the ones at 10 to the 12, the halos at 10 to the 12, I find that at a redshift of 10, there's something like a little under 1 in the observable universe that I'd expect. By a redshift of 4, you know, something like 10 to the minus 3, this isn't so far from the present number density. Right? So they come in very sharply. And if it's just the case that the luminosity function does track halo mass, but we're wrong on the calibration, then what I would expect is to see the same thing. I'd expect to see that just as there's a point for each halo mass, that there's a mass that the mass function is dropping off a cliff. I'd expect to see the same thing for the luminosity, right? But that's really not what this looks like. I mean, what this tells you is that if we're even coming anywhere close in our luminosity functions to measuring masses, that really there's a sharp problem here, that the theory and the observations are telling us two completely different things. And that this isn't a problem of being off by a factor of few in the calibration, but really that the theory is not describing what we observe. Okay? So I think there are really 3 different explanations that I can give you, and I'll point out that all 3 of these explanations really would be interesting in their own right, even though they would point in different directions as far as what we'd want to do about it. Okay? The first, of course, is we could just be wrong when we're inferring these masses. Okay? Maybe some of these detections are spurious. Maybe we can't really measure redshift 8 galaxies at all. Right? Maybe we're incorrectly inferring what the stellar masses are when we try to do this template fitting, and all of the masses are vastly overestimated. I should point out that if that's the case, there are probably two implications this would have. Okay, first, theoretically, if the mass-to-light ratios are substantially changing, this is going to be driven by interesting physics. In other words, this would probably mean, I guess we want to push the mass down, so this would probably mean that we need a much top-heavier initial mass function. So that means that somewhere around a redshift, maybe of 4 or 5, the nature of star formation would have to change, and we'd have to get a much top-heavier IMF. Okay? So this is something that, even if it were purely a question of that, there are interesting theoretical implications. There also, by the way, are interesting implications for how we go about designing surveys. Because the idea behind these large surveys basically comes from the way that we do high redshift astronomy, right? We're always pushing the boundaries of what we can do. So we start out by asking, what is the minimum amount of information that we need in order to infer the properties we care about? If what I care about is a redshift and a stellar mass, what is the minimum amount of photons I need to collect? What's the cheapest way of getting a survey like this? So if it turns out that we're wrong, one of the things that says is that we miscalibrated, right? That we actually need to be doing something different in our survey design. If it turns out templates look much different, maybe any survey that's not spectroscopic in this regime simply can't work, right? And this is something, as we prepare to put this heavy investment into large JWST programs to try to solve these problems, we really want to know what the answer is, or at least sort of think about what would it mean if we've been collecting too little information. Okay, so that's one answer. I should point out I don't think that's the most likely answer. And one of the reasons I don't think that's the most likely answer is because, as I had shown you, the star-forming main sequence that we get actually is exactly what you would extrapolate from lower redshift. So you might hope, if we've reached a regime where the physics of star formation is changing, okay? Yes, as you pointed out, that's going to mean that we now would be wrong in our calibrations. We'd be incorrectly estimating mass and star formation rate. You might hope that we incorrectly estimate them in a way that something starts to look different. You know, we would have to have gotten unlucky to be incorrectly estimating them, but keeping the same correlation. So it's certainly...
If you look at that diagram, though, you fit a straight line through all of the points.
Yeah.
But if you fit 2 lines, you break it at redshift of 4, then those points for the study you're talking about do lie above the line. So why do you fit a single line to it?
Mainly because we don't have enough points at high redshift to constrain it well compared with low redshift. So what I was showing you there really was sort of looking at this extrapolation. If you include the high redshift points, I don't know whether I should say it is or is not consistent with a line, because one of the problems with a study like this is we really don't know what the uncertainty is, right? What I can say is that the scatter from the high redshift points off the line is comparable to the scatter at lower redshift off the line in other studies. But I would be a little bit careful about saying that that's really the same thing as claiming that it's consistent, because we don't understand our uncertainties well enough in a study like this. The simplest thing that looks to be consistent with the points is a line, and that's why I haven't drawn something more complex. But that certainly is no guarantee that a line is the right description. But yeah.
I guess that question, which is, I mean, there are clustering estimates of halo masses, at least for redshift 4. I don't remember if there are.
Yeah, so I have it redshift 4.
Halos there.
These triangles are kind of,
They are.
yeah, these triangles are up here. The problem is at redshift 4. So at redshift 4, everything is consistent. At redshift 4, you can pick all of these methods. You can use clustering, you can use stellar masses directly, and you can use a mass-to-light ratio, and they all give you an internally consistent answer. The problem is, as soon as you get above a redshift of 4, you stop being able to use multiple methods, and so you have to be optimistic. So yeah, it could be that that's just the point that things break down. But on the other hand, if we didn't see that there was a disconnect between theory and observation, I think the conclusion that we would then be drawing is, this is great. Everything is, this is great. Everything is evolving smoothly. If I didn't draw the lines and just show you the points, everything's evolving smoothly. Everything looks normal. This is a good indication that we should keep going in this direction because we're probably getting things right. The only reason that these sort of start to look problematic is because of this disconnect with theory. And so certainly having the data be the problem is plausible, but at the same time, historically, I think the better answer in a case like this is to guess that it might be the theory. So what happens if it's the theory instead? Okay. Well, the second thing that you can do is you can try to get halos to form earlier than predicted. Essentially, I can try to push these lines up instead of pushing these points down. And that's going to need some kind of exotic physics in the early universe, because the way these halo mass functions are produced essentially is taking primordial fluctuations that we can essentially confirm with the cosmic microwave background, and we basically just add Newtonian gravity, a W of -1 dark energy, and cold dark matter. So if you want to change this, you need to come up with some additional force in the problem that causes baryons to clump more readily than we thought, and that means essentially breaking one of those three things, or adding a new force, or something like that. So I think any answer there would be fairly exotic. But I'd also point out that actually the simplest ways of modifying these don't seem to work very well. In other words, most of the ways that people have thought about adding interesting dark matter interactions actually have the opposite effect. They tend to inhibit clustering rather than have clustering happen earlier. Right? Similarly, if you want to do this with dark energy, you could have a W of about -0.94 would get rid of the problem. But that's at odds at something like the 2.5 sigma level with Planck. So it's unclear exactly how you would do it, but I guess the second option is you make the halos form earlier than predicted. And maybe for completeness, the third option is you find a way to really make the baryons run ahead of the dark matter. So that would mean you again would need some force in addition to gravity, but instead of having everything come together, you have to make it a baryonic issue. And that sort of is exotic in its own right. It also probably would carry interesting implications for reionization, because one of the things that goes into reionization calculations is essentially asking how clumpy star formation is. Basically, when I emit a photon in a young star forming region early in the universe, how likely is it to reach the intergalactic medium? And if it turns out that we form all of these stars in small clumps at very high redshift, it might turn out to be a dominant source of reionization earlier than we expect. But for the moment, I think the place to leave this is some interesting answer is going to come about. And whether the answer is on the theory side or sort of the data and the theory that goes into translating data to make it compatible side, really either of those tells us something exciting is about to happen. And we should really look forward to JWST taking spectra of some of these and trying to confirm whether we've got it right. So that's one problem that's kind of unsettled. What I want to do in the remaining time is tell you a little bit about why mass downsizing also seems to be a little bit surprising. And here maybe even some places that we might be able to explain it better. So I had mentioned before some of these halo mass functions, okay? And this is another way that I can look at the halo mass function. What I'm showing you here at different halo masses is what fraction of the redshift 0 population, what fraction of the redshift 0 number density exists at a given redshift, okay? And so it looks like the more massive ones come in later and assemble later. I should caution you, though, that this title is a little bit misleading. I probably should say that big halos finish assembling later, because at redshift 10, a halo of its 10 to the 10 solar masses probably is not going to be 10 to the 10 at redshift 0. Probably what's going to happen is through merging, it's going to grow and be part of one of these larger ones, okay? But what I can say is that you reach the present number density of more massive halos later than you reach the present number density of less massive halos, right? So in that sense, you still might expect that if I look at the galaxies inside these, you might expect that sort of these small galaxies get an earlier start. It's easier to make a small galaxy earlier in the universe because there are more small halos early in the universe, okay? And this is well settled theoretically, right? Okay, secondly, we can look at quiescent populations. So what I'm showing you here is just the fraction of galaxies that have become quiescent as a function of stellar mass and then as a function of redshift. And what we see is that both at high and low redshift, essentially the more massive galaxies are becoming quiescent. They're finishing their star formation first, right? And this is another version of what I showed you before, where I showed you that the more massive things are star forming at high redshift, but they're not seen at low redshift as star forming galaxies. They're only selected as some other kind of population, right? And this also, by the way, I should mention, tracks with a passive population that, so I was going to say at redshift 2, but actually from discussions earlier today, it sounds like I now get to say at redshift 4. There's a passive population that seems to be comparable in mass to what we've been inferring at redshift 6 for the star-forming ones. So that's maybe, again, another hint that sort of, it may not be the data that's off, okay? But essentially, at least as far as turnoff, it seems like the more massive galaxies are finishing their turnoff first. And the last thing, of course, everything comes back to the star-forming main sequence, okay? That when we look at this slope, one of the things we find is that the slope is less than 1. So that as we go toward higher mass, we have higher star formation rates, but we have lower star formation rates per unit mass, okay? And one of the ways we can think about that is essentially what fraction of the existing mass of a galaxy is being made per year at the current star formation rate. That's one way of kind of asking roughly how long you might expect it takes to make stars, right? And what we find is that the lower mass galaxies have higher star formation rates per unit mass, right? That for them it takes closer perhaps to 100 million years at the star formation rates we see in the high redshift universe to make all of their stars. For the more massive galaxies, that becomes a little bit closer, that's becoming closer to 1 billion, okay? So, okay, these are all three then things that now seem to be pretty well measured, either observationally or pretty well calculated theoretically. We put them all together, and what do we get? Okay. Well, we get that the big halos sort of are assembling later. So the big galaxies seem like they start later. They take longer, but they finish first. So again, something in this chain of logic kind of has to be broken, right? Okay. Well, what's wrong? Well, there are a few ways to answer this. I think. First off, I should point out that 2 of these are really observationally driven, right? And one's theoretically driven. So, lacking any other knowledge, just sort of thinking historically about astronomy, if you have to guess, you should probably guess that it's the theory that's broken. Particularly because this seems like the kind of problem that, just like with these impossibly early galaxies, right? Seems like the kind of problem that's maybe just telling you we need to assemble massive halos earlier in the universe than we thought, and we need a mechanism for doing that, okay? On the other hand, I should raise a second possibility here, which is that we've been talking about the star-forming main sequence in terms of how galaxies grow. But maybe that's not a full description. Maybe there's some other process going on there. And one of the strong hints that this could be the case is that if we look, so there are several different things on here, but what I want to show you actually are these blue points, because they correspond to sort of halos with one galaxy in them, okay? And what we're seeing here is essentially how efficient they are, what fraction of their baryons they're able to make into stars. And the regime, when we look at the star-forming main sequence, essentially is the left side of this. It's down here, okay? What this is telling us is that as the halo is getting more massive, it actually is doing a better job of taking matter and converting it into stars, right? And this is sort of the opposite of what we find with the star-forming main sequence. The star-forming main sequence tells you that for new star formation, that we seem to do a good job observing, and that, for new star formation, big galaxies are less efficient at making their stars. But somehow when you put everything together, we're finding the opposite, right? Maybe another way to sort of show you this disconnect. So I had a great summer student, Dominic Yerk, who just sort of put this together in the last few months with me. And what we did here, this is just showing you 3 galaxies evolving along the main sequence. And we start them with a spread of a factor of 10 in mass, and we let them evolve for a few billion years. And what we find is they get closer together. That the low mass ones are catching up because they're more efficient, right? And if we think about what this would do to observe mass functions, okay, we can start, the red here, we just took an initial observed mass function, a little under redshift 1. And we just let every galaxy evolve along the main sequence to see what would happen. And what we find is that the low mass ones grow more quickly than the high mass ones. They're catching up, and so the mass function gets steeper. But if we actually look at observations, the mass function is, if anything, getting a little bit flatter, right? So what this is telling us is that even though the star-forming main sequence seems to do a good job of telling us about how new stars form, it can't be the full story when it comes to mass evolution. Okay, so then we started asking, well, we know these are all complex processes, right? But what is the least complex thing we can do to try and repair this difference, right? What's the least complex thing we can do to try and repair this difference? So, first thing we know some galaxies are becoming quiescent, right? Maybe we can try to solve this problem by just turning off galaxies in order to get everything to match. So, okay, we asked, you know, we picked, oh, sorry, yeah.
So
this one?
Yeah, for this thing, so you're using some main sequence that has some slope. So what slope are you using there?
In this case, I think we're using, it's actually a very slight time dependent, so we're using the fit in this paper that Josh and I had that kind of is the, we're using the consensus fit that I showed you earlier. So it ranges from about 0.65 to 0.8, something like that, depending upon the redshift.
So
there's a slight redshift.
If you use a slope of 1, then the mass
If I use a slope of 1, the
work.
mass function would uniformly move to the
Yeah,
right.
and I think actually, so in the most recent studies, including from Forge, if you go low enough masses, we always find slope is 1. And at the high mass end, it does flatten out a little bit. And so previous studies, if they only were probing the high mass end, they would find the slope less than 1.
Right. So this is primarily, but this is primarily, so down here we really don't have an answer at high redshift. The best thing the only thing we know how to do is extrapolate, right? It's really up here that we sort of start to have an answer at high redshift. But that's right. So if you had a slope of 1, this would be flat. If you had a slope greater than 1, if you had a slope of 1, it would be a constant. It would be a constant slope. If you have a slope greater than 1, right, then it would flatten like we see. If you have a slope less than 1, then it will steepen. At least the studies on the high mass end are all giving you slopes less than 1. And so that's what we've done here. But yes, if you can find a way to get the main sequence to have a slope greater than 1, that would be another way out, right?
Well, I mean, it just has to be very close to 1.9, 1.1.
Well, I guess to get it to flatten, it really has to be a little bit greater than 1, if that's the only effect. To make it flatten, the slope has to be greater than 1. Right?
So to maintain the same slope,
To maintain the same slope, it would have to be 1.
It would have to be 1.
Yeah.
Modulo mergers, which have a small effect.
And that's what I'm about to get to, yeah. So we then sort of asked, okay, what are the things we have to introduce to fix this, right? And the first thing we tried is turn off, okay? How many galaxies would you have to turn off to fix this? Because we're just trying to build the simplest empirical model we can, right? And the answer is you need to turn off a lot of low mass galaxies, but that's not what we see. Okay, so that one doesn't work, okay? Maybe a better candidate then is to think about the effects of mergers, right? So again, for the merging now it's a little bit complicated because typically the simulations of mergers are thinking about the dark matter and we have to paint the baryons on in some way, okay? So what we did, I'm showing you an example from the Millennium simulation, but we essentially took a merger rate function that looks like this. So we just have some slope and some normalization. There are 2 parameters that go into this. And we looked at some different parameters for what would happen, okay? And we also have to match halo mass to stellar mass. So that's not so far from linear for most of the regime we care about, but that also breaks down a little bit on the high mass end. And this starts to matter because when you deal with mergers, you also care about the more massive halos because there are a lot of mergers between very massive things and very low mass things. And so you're kind of sensitive to what this high mass cutoff looks like. But okay, we put these 2 things together. Okay, well I should point out first off that mergers in isolation do flatten things. So we started with some initial mass function. We ran only mergers. It appears that you're missing mass. Well, what's actually happening is you make some clusters out here in the tail. Right, that's where this missing mass is going. But the main thing that mergers do is they get rid of things on the low mass end, right? And it turns out that if you put everything together, that at least comes pretty close to solving your problem. So what I've done here is I've taken an observed in red, I've taken an observed mass function, right? If I just evolve it forward using mergers only, it gets flatter. If I evolve it forward using star formation only, it steepens. We put these two things together, I get this blue curve, which has at least the right slope for the yellow one. So this is the merger rate function that's used in the Millennium simulation. Okay? But there's actually a fair bit of wiggle room in choosing those parameters. So if we look at other merger rate functions in the same parameter space, similar merger rate function, just pick a little bit different slope or a little bit different normalization, then I can do the same thing and I can actually get something that does a good job of matching the observed mass function. There's some bits of parameter space. So the particular one, the Millennium simulation, isn't quite in this parameter space. It misses by a little bit. But I can pick similar looking functions that seem like they would have equally plausible physics with just slightly different choices. And we can actually make it work. Okay? And I should point out, by the way, that we make this work in a little bit of a surprising way, because we've treated the merging as an entirely independent process from everything else that's going on here. I expected that in order to make this work, we'd actually have to invoke some kind of feedback, or we'd have to assume that the star-forming galaxies were preferentially more likely to be involved in mergers or something like that. And we can make empirical models where that's true and get everything to be consistent. But we also can make models where they're just completely independent processes. And that's nice, because we started with this puzzle with the star-forming main sequence where we thought it should depend upon all these environmental factors. But it was actually giving us this simple description universally of star formation. So it's nice that it turns out that you might be able to solve this problem still allowing the star-forming main sequence to have that property, and still allowing them to be separable.
Sorry, quick question about this plot. Is there a quick intuitive way to understand how the parameters you prefer for the analysis differ from Millennium? I mean, you get a slope and a normalization.
I think the biggest answer, I think you can convert from Millennium to ours if you just take the most massive galaxy in the Millennium survey and you multiply it by a factor of 4. The problem is these are very sensitive to the high mass cutoff in halo mass. Okay. And that's a somewhat arbitrary choice in doing these simulations.
Okay. But the merger rates depend on halo mergers, right? In the Millennium
Yes.
simulation.
Yes, it's halo mergers, but the point is that sort of the mergers between big and small things are very important here. And so just changing the mass of the most massive thing in the box turns out the most important thing is a normalization, and just changing the high mass cutoff changes the normalization substantially. And so that's why these aren't particularly, this isn't a particularly bad answer. It just sort of says that the high mass cutoff used in Millennium isn't quite the one that matches. And I wanted to run this for some of the more modern ones. The main problem is just that they describe their parameters slightly differently, and so it turns out we have to rewrite some things basically to convert the description of mergers from Millennium to something like Illustris. But given that they get similar halo mass functions, I would expect to get a similar answer, at least intuitively.
So when you talk about the Millennium merger rate, that's just the rate at which halos merge.
Yes.
But the galaxy merger rate should be quite different. It's because halos, accrete a big halo accretes a little halo, and then you call it a subhalo. That can orbit around for big years.
Right. So what we're doing here is essentially, we asked what's the very simplest thing we can do. We basically said when they come together, this is basically taking us from two small things to one big thing. And if they're sufficiently unresolved, that's going to be true. As you get toward low enough redshift where you might be able to resolve them, then that will become false, and it will become important that the one's orbiting the other, right?
And groups build up over time.
Right.
So these are halos that are merging, but the galaxies themselves aren't merging.
That's right. Yeah, that's right. So when we talk about a merger here, we're just counting mass. And so in that sense, we're not trying to distinguish between a subpopulation that orbits and a subpopulation that entirely gets mixed. Okay, so what does this kind of tell us, right? Well, it tells us first off that, the main sequence, certainly it exists, okay? It seems to be telling us something universal about how new stars are forming in galaxies, right? But it can't be the full description. And that if you add in merging, even if you allow that merging to be unconnected, somehow you have to account for merging in order to go back and repair this problem, right? And it's a little bit of a weird answer, right? We started out with this problem where the main sequence is telling us that small galaxies are more efficient. But observationally, somehow the large mass galaxies are more efficient, right? We might have hoped that the solution to this would be to find a way to speed up the massive galaxies or to slow down the low mass galaxies. But that's not actually the way this works, okay? What we're doing instead is just getting rid of the small galaxies. So one way to see this is if we look at these merger rate functions. What I'm showing you at the top, these are sort of star-forming galaxies of a given mass and redshift, and at the bottom, these are galaxies that we quench and sort of fix at that mass. And we basically ask, what is the probability that one of these galaxies will merge with something larger, whether it's a larger galaxy or just sort of become part of a cluster, we can't tell, but will merge with something larger by redshift 0, right? In other words, how low in redshift do I have to go until if I see, say, a 10 to the 10 solar mass galaxy, it probably survives by itself till redshift 0? And the answer, at least to me, was surprisingly low, right? That for the star-forming galaxies, maybe at 10 to the 11 it's likely to survive, even for a quiescent one. If it's 10 to the 11 at redshift 3 and then turns off, which are some of the most massive things we see, there's a good chance that it ends up merging with a larger group or something like that by redshift 0, okay? And certainly on the lower mass end, basically this tells us that all the galaxies that we're seeing that are surviving till today really come in fairly late, that all the ones that we see that get made early are very short-lived. So the solution that we come up with for this problem is really that we're not making the large galaxies more efficient. We're just removing all the small ones, and so they become the most efficient by default. And that's how we kind of invert this hierarchy and go back to making the more massive ones earlier. So it's not the solution we expected. I also should caution, there's no physics in this right now, right? We simply asked, what do we have to do empirically to make this work? How hard of a problem is it? And frankly, I hoped it would be a harder problem, right? I hoped that we would find that the minimal thing that we needed to do was to start invoking some strong feedback between different processes, and that would be a good way of letting us start building some models. The fact that we don't, the fact that, it's at least consistent with these all being independent processes really isn't so nice, because we'd like to know if this is the right answer. I guess there are some observable consequences, right? What you can do is, this makes a prediction for merger rate functions. But those are still hard to measure, because the most sensitive piece of the merger rate function is really a merger of things at very different masses. That's the number we'd like to nail down. But there are very few surveys that are capable of getting a merger of things that are different by 3 or 4 orders of magnitude in mass. Certainly at high redshift, there's really no way to do it, right? So, okay, this is perhaps testable. I would, though, point out that for the impossibly early galaxies, this is still not a solution, because this does not let you make more massive things earlier. All it does is it gets rid of the less massive things that you're making alongside them. So there, it still seems like we're going to have some kind of sharp problem. And sharp problems are great, because what that really means is, in the next few years with the JWST, we're going to be pretty rapidly forced into one of these conclusions. Either that we've completely misunderstood high redshift galaxies, and that's really exciting, or that we've completely misunderstood halo formation in that part of cosmology, and that's really exciting. And in the next few years, we should be able to find out which. So let me thank you again for inviting me and taking questions. Thank you.